University of South Carolina on fractional analog of Brooks theorem. Thank you.
Thank you. First, let me thanks organizer for inviting me here. So my topic is fractional analog of Brooks theorem. And Brooks theorem is a classical theorem in graph theory. It should be included in most graph theory textbooks. I don't know which one will control. This one control. Oh, can you use this one? This okay. It's fine. I think this okay. Okay, so let me just introduce the thing first. So G is the graph, and V is the vertex set, E is the edge set. And here we want to consider simple and connect graph. This one. Thank you. Right, and delta of G is the maximum degree. So degree means you take each vertex and see how many edges are associated with it, and you take the maximum. Alpha G is the independence number, which means the maximum size of independent set in graph. And omega of G is the click numbers, which is the maximum click size in graph. Half G is the chromatic number. Yes.
What's a click?
Click is just the completion of graph.
Oh, okay.
So you take an inducer graph to see it's complete and follow that lead. Half G is the chromatic number. So chromatic number is a little word to describe. Is the way that you color the vertex in some colors, and that you want to make sure that each vertex is adjacent to each other, and they are still different colors. And you want to make the color number as small as possible. That's the chromatic numbers. But let me just give you an example. Okay. Oh, that about we'll spend more time talk about it. The fraction of chromatic number. Okay. We'll get that thing later. So now here is the graph, the C5, 5 cycle, and the maximum degree is 2, because each vertex has 2 edges, so it's adjacent to it. And alpha of C5 is 2, because you can have you can take a pair of non-adjacent vertices, and you cannot add third one. You must add third one with the edges. There's no triangles, but you have edges, so the click number is also 2. Chromatic number is 3. If you will try to color graph in 2 colors, will not work. You have a pair of vertices receive same colors, but you can use 3 colors easily. You can do 1, 2, 1, 2, and 3. The next one, okay, the fractional chromatic number will show is 2.5, and we will give a definition and see why it's 2.5. Okay. So the Brooks theorem is just if your graph has maximum degree delta, and then it can be colored in delta colors unless G is a complete graph or R cycles. Now here is a complete graph. Okay, so you have vertices. Each pair have edges. This is a complete graph of 5 vertices. The left one, the right one is R cycle is C5. For this one, it's easy to see. You need 5 colors to color it. Okay, from color it. And the left C side you need 3 colors. In this case, now if you consider what the maximum degree, of course each vertex will have same degree the same. So they all have 4 edges associated with one vertex. So the maximum degree is in this graph is 4, and the maximum degree of the C5 is 2. So it's not satisfied, but that's the only exception. That's Brooks theorem. Fractional chromatic number, okay? Now this time so we still use some colors, but now each vertex can receive a set of vertices instead of just one color, a set of coloring. So for example, here is 5 colors, 1, 2, 3, 4, 5, and I can color each vertex like 1, 5 with 2 colors, 3, 4, 1, 2, 3, 5, and 2, 4. If you look at it carefully, for each edges, okay, and the vertex are received, the color they received is a disjoint. That's the so-called the 2 coloring. And you can use 5 calories, so apple is 5 to calorie. And now we consider ratio. So the fractional number is defined this way. You take all the number of colors you use divided by, for each vertex, how many colors you receive. And you take the Ephraim. In fact, you actually, there's always some color in achieve these numbers. You can replace Ephraim by the minimum. This example show you can have 5 to carry for C5. And you can show this is the best possible. There are some basic inequality related to the Carolina numbers, fractional numbers, the clique numbers, independent number. So one is that, okay, the fractional number is always bounded by Carolina numbers. This is just by definition, because by definition, if you use each vertex with one colors, then that exactly give the Carolina numbers. The other bound, it's easier to see the clique number. You can much better than the clique number. So it's just bounded by row by clique numbers. The other side is that why this fractional number is greater than n over r of g, because if we consider the vertex with the color 1, vertex with color 2, vertex with color 3, all those different set of vertices are independent set. And they should be less than the r of g, the independent numbers. And you add them together, you should cover all vertices by b times. And that's by the ratio definition. You can easily see that the fractional number is greater than n over r of g. Okay, so in this example, okay, y is to 5. We should just show you that 5 to carry. Now, if you look at the independent number is 2, and this equality says at least 5 over 2, right? And this 2 bound give you this type. That's why the fractional number of C5 is 2.5. Okay, so here is our theorem that proved. Given any connected graph G, and if the fractional number is at least the maximum degree, and if and only is the graph is one of the following graph, okay? The first graph, of course, the complete graph satisfied. The other one is odd cycle, okay? That's actually really come from Brooks theorem, okay? The third class of graph is that if your graph has a large clique of size delta, and the fractional number at least this much. Now, it's strangely that other graph, okay? The third graph is full of C8 square, the square of the 8 cycle. The fifth one is the 5 cycle, you take the strong product with K2. I will explain what these 2 graphs are. And this is the complete list, if and only, okay? And this is 2 exception graph I will show you. Here is the square of the C8 cycle. So you take an 8 cycle, you connect each pair with this at least 1, at most 1 and at most 2. Connect them, and you get this square graph. This one you replace the C5 by clique size of 2, and each edge is replaced by complete by paragraph. So that's this graph. For this one, you can easily see that the fractional number is 4 and equals to the maximum degree. And here, this one maximum degree is 5. The fractional number is 5. Why you can determine the 4 and 5? Just because you can easily check the independent number of these 2 graphs is also 2. And the number divided by the 2, let's do a low bound. This is called 4, 5 times 5. And on the other hand, you can easily give a good coverage. Okay, so actually we can show a little stronger result. So if assume the graph are not those graphs which is listed, and then you can prove that the Carolina number is not just less than the maximum degree, actually less than a function of the maximum degree. This one is not optimized, so you can easily get a better bound, but we should show there's a gap there. So in some sense, there's no graph between this interval from bigger than delta g minus this function, less than delta of g. There's no graph satisfied have fractional number in 4 in this interval. Somehow you have a gap there. This kind of price for us, okay? we do need the maximum degree is at least 3. Otherwise, if maximum degree is 2, just the path of union of paths and cycles is easier to figure out, but not satisfactory. So we do this condition. Okay, so let's just look at there's some conjecture with this problem. So for the maximum degree is 3. Actually, there's a Heckman and Thomas in 201 conjecture. The practical number is at most. If the graph is triangle free and the maximum degree at most 3, then the fractal number is at most 3 minus 1/5. This is the best possible, and that's the graph. This is called the generalized Peterson graph. The Peterson graph is C5 with this shape, but this is the C7, a similar construction. And you can see that this one, the independent number is 5. So you take 1, you take 5, and about the equality says this actually you can show this fractal number is exactly equal to 14, so this is 2.8, the same thing as 3 minus 1/5. And this is the carry, how you do it. Okay? You can put down I use the A, B, C, D, so because it's 1 to 9, that's 9 colors, then A, B, C, D, E, F, right? Plus 5 colors, so you total have 40 colors. That's a proper carry. Heckman and Zhu in 209, they didn't prove this conjecture, but they said they proved some outbound. They said, okay, I cannot show it's at most 3 minus 1/5, but I can show 3 minus 3 over 64. After we read this paper, and actually we improved a little bit, 3 over 43. Okay. That's the last year. This year we'll consider for all graph with the maximum degree at least 4. So there's another conjecture with this problem. It's by Borody and Kostachka, that if G is a connected graph and it's K data free, and the maximum degree is at least 9, then the chromatic number is at most data G minus 1. So in some sense, you can improve the group theorem by 1 if their data is large enough. We also need this condition. Okay? And if this condition is true, this is possible. Okay? And there are always some examples show why this cannot get better. Now this graph is the C5 strong product with K3. So you replace each vertex by a triangle. You replace each edge by a complete parallelogram, and you do same thing structure. And you can show that the maximum degree is 8. The chromatic number is also 8. And the fractal number is 7.5. But here we talk about the chromatic numbers, so you cannot improve. Okay, well, good thing is Reed in 1999 proved this conjecture is asymptotically correct. So asymptotic means if your data maximum degree is large enough. How large it is? Well, they didn't say, but you can read that paper, and their proof implied at least hundreds, okay? 100, and then that's true. And proof is the probability method. And you know, if you use the probability method, they always have to be large enough. And it's essentially you cannot generalize this method to small ones. So our idea is to prove our theorem is we try to consider the minimum counterexample. So assume the answer is not correct, they should have some graph which satisfy all these things here. And we assume the graph will have the minimum number of vertices. And first of all, we assume it's maximum degree K, and it's critical number is K minus 1. Then we also assume that the fractional number is at least K minus this number that's equal to 1. So, and it's not two graphs. And then we'll show the set is empty set, okay? So that's what we now go. So, the middle color example have some properties, okay? Oh, this is actually the same thing, okay? Okay, so the properties. So one is that this graph should be KK free, okay, just by definition. And each vertex at least K minus 1, otherwise you can delete this vertex. You get smaller counterexample. because it's linearity, we have this property, and the graph have to be connected. Okay. Now, if you take any subgraph, then the subgraph should not satisfy, so you should have smaller. Otherwise, if we plan the set, it's no longer the minimum. And with this property, the idea is, okay, I take one vertex, I will try to find a set of neighborhood, find 3 of them, okay, if there's some 3 of them, those are no edges in that neighborhood, then you have to use one color. And then that will save me some color in X. If there's no such triangles, I can find 2 non-edges and you color in 2 colors. This also gives save me some color for X. And each one will save me 2 colors, so I have some freedom. And I want to color this for a very large set. That's the idea. One technique is use the so-called vertex identification. So each time you really contract a set of S and replace by one fat vertex. And that's all what we are trying to do. So suppose if you contract these 2 vertex like this, after contraction you get 1. Okay? And we are able to use this contraction to get a key lemma. This is the lemma we spend like how many pages? 10 pages maybe? Yeah, it's actually very hard to prove. Okay? It says if it's if you look at the neighborhood graph and it's given size 2, and then you can find 2 sets, and such that you can contract them 2 edges, and the result graph contains no k plus 1 minus. This is the complete graph on k. Actually, it's almost complete graph. This is the 1 edge less than the complete graph on k plus 1 vertices. So here, k equals to 4, you also can forbid this graph. Okay, this is the complete graph minus 1 edges. Okay, after the contraction. So this you can choose this way about this. Okay, then you can do the past neighborhood. You can define, okay, the set we contract, I will call it S of X, basically. And then we say, the neighborhood, the past neighborhood, you start from U and V. If you can find a path, such as the first vertex and the last vertex, okay, then those actually be in S of X. And then easily see, you can count how many edges you have, okay? So we can define this graph, it's a super graph, and if there are distance, the path distance is 1, 2, 3, 4, 5, 7, and then you connect them. This graph has more edges. And this graph, you easily to find the maximum degree, and the maximum degree actually turn out just, okay, use the easy calculation is the bound we want. Now, the next lemma says, suppose this graph can be m color, and then you can use this color to show that fractional current number is less than k. That's how we get. And if you plug in this m by its maximum degree, and then we just get the 0. That's the basic idea. How many minutes do I have?
10 minutes.
Okay, so
10 minutes.
So give some ideas. Okay. So okay. So some ideas. Okay. So okay. So we will try to contract. Okay. So one color. Let's say a few colors. You take a large set, and then they are far away. Okay. And you contract this with one colors, and you will say the result graph is still data colorable. Okay. So you remove one, and then you also contract one vertex. Okay. Like this. Okay. So. And this graph is kk plus 1 minus 3 just because of our construction, and all vertices by 2 colors have degree at most k. So now we can use the tool called the Gala's lemma, and the Gala proposed lemma in 1963. So if G is a k-critical graph, then you look at the subgraph, it deals the vertex with degree k minus 1. We call the Gala forest. Gala forest, Gala forest is a graph that you can consider block. So basically, a block is the maximum subgraph which is two connected. And each block should be either complete graph or other cycles. And Gala's lemma is stronger than root 0. It implies root 0. So we use this lemma, okay? Now, the clear graph should look like this. This part is the gated forest. This is the two fat vertex, one red, one blue. And for K graph, K greater than 5, any new vertex L must at least should be the K minus 1. This is just by our construction here. And all vertices but 1 in L adjacent to these color vertices. I use this one, and we can actually cover an X, which is original before do the construction, okay? And you get these structures, okay? So all we need to do is say we need to forbid this kind of structure. And this structure, okay, so that's vertex X above, two little blocks are all connected to the same vertex X. If they connect to the different X, okay, so you say you have X and Y, and then you get a path from X to Y, which is the length of 1, 2, 4, 5, 7. But we forbid those, so this cannot happen. That's why you only have one vertex. And then you can continue degrees, and you get a construction. You will reach the configuration. So that's our goal. Okay, so let's return to the lemma, okay? And we want to, some way you look at the neighborhood, find a pair of 9 edges, you want to construct them. And after constructing the result, contain all this complete graph minus 1 edges. Okay, all right. So what if it fails, what will happen? And we get very nice characterizing of what will happen. If you look at the complete graph of the neighborhood graph, so you first take a neighborhood, okay? Then you take an induced graph. Then you take a coupling. And this graph must be either a K4, a path of less 4, and this is for degree is 4, or it's a C4, okay? It could be degree 4 and 5, or a tree like this, okay? So those 9 is form a tree, 5 verses. And that's only 3 cases, I think 4 cases, okay? This one the second one have 2 cases. For each one, you can build up the original graph, okay? So this one, for example, this is possible. This is the last graph we have people. We're very sure if the graph contains H10, this is not K minimum, you can reduce it. And then actually there's only one way you can extend this graph. We want to show, okay, here we give a 9 to carry, sure this graph is 4, the fraction per number is most 4.5, less than 5. Here is the carry. And then if for the other type, if it's the C4, we show the graph is either this is the one of the second graph, okay? Or this one minus 1 edges. And then you can do you have some edges going up because it's 2 connect graph. And then we'll show that if we graph on this graph, then we the other part is it should be the fraction number should be smaller. Okay? So one tool is what's called expansion lemma. If you have one part, G1, G2, they join 2 edges, 2 vertex, and the fraction number is bound by this. So G of 1 here, but G2 you plus 1 plus UV means you add 1 edge UV, and you divide by UV, you contract UV. And so all you need to do is the information here is only depend on G sub 2, okay? And then if the edges is easier, okay? And we use this tool, we can show, okay, well, why you cannot have this. If graph have this now, you add these edges, and we say this is 4.5 colorable, and this is also 4.5 colorable, so 9 to 5 colorable. And this is contracted with 2 vertices, and this is how we can reduce this graph. So just like in the 4-color theorem, they have a lot of unforbiddable configurations, and you show all the avoidable configuration is reducible. So we do try to do similar things, okay? And we say all these graphs is you cannot avoid, okay? But then we say, oh, this graph actually you can reduce. So this is a few graphs for this case, okay? And we can do the same similar things. For K equals 3, and if the graph is C4, we have 3 graphs, okay? So we have 9 graphs, and then we want to reduce all of them, okay? And a lot of work. Basically, you want to contract some of them, and for each configuration, you'll find the colours. And I think that's all.
Questions?
Okay.
At the beginning, you said the infimum is actually a minimum. If
Yes.
if the minimum is 4/3, does that guarantee there's a 4/3 bell ring, or is it possible there's only an 8/6?
It's possible could have 86. Yeah, it's to prove it that there are several equivalent definitions for the fractional parametric numbers. So one way is just add that given. Okay, you take the minimum of the infimum. Yeah. Another way is use a linear program. So you set up a linear program, and you say okay, what is the optimal values? And because the linear program is always, if once it exists, it's always achieved by some rational functions. That's why they prove it's the minimum always exists. You can put it on. It's not trivial, but there's a book available online. If you Google, you can search fractional gram theory, and that's give all the proofs. Yes.
How hard is the same ideas, but now using direct graph?
Direct graph, even this one, we didn't appear, we said it's a proof, but it's a lot of cases we are not solved. Did I? Should one more page, I don't know. Oh, yeah. Okay, so actually I will talk about the problems here. So it's not related, okay? So we can say the gap, okay? What is the maximum gap, okay? Possible gap. So for 3, Heckman Thomas actually conjecture, it's 1/5, okay? And we don't know that. About the 4, okay, so Broad's conjecture says actually when maximum degree is greater than 9 should be 1. But we don't know, okay? And each number actually we don't know. Like 4 is this 1/3, maybe. How about maybe 5 I didn't mention, but I think 5 or 8 should be 1/2. I suspect it's 1/2, but we have no proofs. So even for the graph case, we can solve it. Certainly, I think so. You can consider the direct graph version. I think it will be hard.
Yes.